right. Hello, everyone. We are happy to have Edgar Dobriban as our speaker today. So, Edgar is, before I introduce him, just to give you a little bit of background of why we're having the seminar online. There's a massive storm in the East Coast and the Midwest, if you don't know already. Flights are basically all canceled. So, unfortunately, we couldn't have Edgar in person, but he's been very kind to be willing to have all the meetings as well as the seminar over Zoom. So a little bit about Edgar. He's an associate professor in the Department of Statistics and Data Science at UPenn with a secondary appointment in the Computer and Information Science. He obtained his PhD at Stanford in 2017, and his research interests are the interface of statistics, machine learning, and AI. He's very modest and didn't put all of his many awards, so I'm gonna say some of his awards. He's received the Courier Award, Bernoulli Society New Researcher Award, the Sloan Fellowship, the COPS Emerging Leader Award, the Army Research Early Career Program Award, basically all early career awards you can possibly get. Edgar has received them. Recently, the Peter Garvin Hall IMS Early Career Prize as well. So we're very honored to have Edgar speaking to us. He's happy to take questions as they come, especially given that this is over Zoom. So if you're unclear about anything, please feel free to raise your hand, and then I'll unmute you and you can speak. Thank you.
Great, great. So thank you very much, Armin, for the very kind introduction, and thank you for the invitation as well. I'm really, first of all, I'm honored to get a chance to speak, and I'm sorry that I cannot be there in person. It's literally like, Saturday afternoon, Saturday night, my flight for Sunday night was canceled, and there was no options, no other options. And there was a little bit option. There was another option to reschedule for some later time in the semester. There was an opening, but I already committed to be in another workshop at that time, so it couldn't make it work. So I apologize. This is the best kind of least disruptive way to do it. And I know it's not great. It's kind of like it gives COVID vibes, but please at least at least it can we can make it happen. And I'm still glad to talk to people over Zoom. So please feel free to ask questions. Also, I really glad to virtually visit, and I was very impressed. I talked to some of the junior faculty and in the department, and I was very impressed with their work. There are so many interesting ideas, so it's kind of really vibrant environment. So yeah, today I'm happy to talk about kind of a topic that kind of relates statistics with generative models and synthetic data. So as we kind of know, artificial intelligence is really emerging as an important technology, and we have a lot of kind of success stories that a lot of us kind of probably use on a daily basis, like language models, ChatGPT. Now there are models that can write very good code. This is a screenshot from kind of Claude Code. It's really amazing at how well it can write pretty complicated software. And there are models for image generations, like this one is kind of like I asked it to generate an image of a person riding an elephant riding a bike. So it was a while back. It's not that great, but they got better. And we also got the community DeepMind got very good at protein structure predictions. Is an example of real and predicted protein structure overlap. So it's kind of really good. And in fact, the AI models are getting very good at math as well. And I was really quite impressed. They're very helpful in one of my projects. I wrote a kind of 10-page short paper on arXiv. It's just a kind of note of how I was able to use ChatGPT to help me, the GPT 5 Pro, the kind of advanced version, but help me with a problem in robust density estimation. And if I have time at the end, I'll give you a little bit of detail about it. But they are really getting quite good at math as well, even like pretty advanced stuff. So I think it's really kind of a development. But at the same time, there are also problems, like they make very silly mistakes. Like this is just kind of online in social media. People are like testing the models, and sometimes they find like very kind of silly corner cases. Like initially, people were like, "Oh yeah, can I can the models count? Can the models count letters? How many R's are there in strawberry? And of course, there's three R's, but the model, because it's really some sort of model class of transformers. Some sort of model class. It doesn't. It's not necessarily. It's not an algorithm that counts. It's a model. It doesn't do that well. But then they fix that. But then people found out, yeah, it overfit because if you change how many strawberries are in there, then it also has three. So it's kind of like this is overfitting. And the LLMs, language models also generate security mistakes, and some vision language models, they generate crazy looking pictures that don't make any sense. So partly it's great when it works, but there's no guarantees that it works. So sometimes it's really bad. So I think that's kind of like describes AI pretty well, that it's sometimes really great, sometimes not so great. And kind of to try to understand the interface between kind of this AI and statistics, one perspective is that of synthetic data, where you kind of whenever you prompt a model, it generates some data. I refer to it as synthetic data. So for instance, there's a lot of excitement in this is from some paper in kind of I think Nature Communications, where they kind of describe a methodology where you can ask the model to generate various types of radiographs, and then you can use that for all kinds of different purposes. But we know that sometimes it doesn't work, right? So how can you really trust it? That's kind of like what I'm trying to study in this talk. And this kind of connection of the generative AI and the synthetic data with statistics is really just an emerging area. There's only a few papers. So I have here one paper from Shihong Lin and Jessica Grosball from 2 years ago in Nature Genetics. They kind of make a connection to using synthetic data with some in some predictive inference models, and also a paper from Guang Cheng from UCLA that kind of has a utility theory. So our work is really quite different. So I will not go in that much detail, but these are really some kind of early work, and there's only a few of them. So we know that synthetic data is imperfect. So that's really the question. If it's imperfect, how can we use it? How can you use synthetic data in statistical inference? So this is what kind of we set out, and now we have several papers on this with this team. So it's a kind of a Professor Yaniv Romano from the Technion, and Yaniv's students Meshi and Roy, and the postdoctoral researcher Yonghun Lee, who works with myself and with my colleague Eric Chadgan. So this is the team, and we kind of is really excited to work with them. They did a great job. Happy to talk about the results. So, okay, in short, what we've done is we developed a method called GESP, which is short for General Synthetic Powered Inference. So this method is sort of a wrapper method that, once you have a statistical inference pipeline, you can use GESP to allow you to leverage the synthetic data in a safe way. So it kind of enhances the sample efficiency, combining the real and synthetic data in some sense. Of course, like the naive thing would be just pull the real and synthetic data, run your method on it, and see what happens. But we know that the synthetic can be really bad potentially, so that's not kind of safe. So we have a kind of small wrapper around it that tries to address this problem. And it's kind of a general kind of decision theoretic loss minimization based perspective. So because of that, we are able to handle a lot of problems in hypothesis testing and constructing prediction sets and risk control and multiple testing. And depending on how much time I have, I will show you applications to AI on comparing two different language models, which model is better when you have only very limited data, because you need to have limited data because you cannot use the data that's already on the internet that might be contaminated. So you need to have new problems, and humans need to write the problems, so it's very limited. Potentially some interpretability if I have time, some protein structure prediction, and outlier detection. So it's kind of a general framework, and I'm pretty excited because it really even though it's very simple, it has a lot of potential. Okay, so all that was just the introduction and the setup. And kind of now we come to the more kind of precise mathematical formulation where I'll write down to you everything completely and all the details, and hopefully it will make everything clear. So we take the perspective of kind of statistical decision theory, where we want to control a risk measure that's defined through a loss function over some population. So that's kind of the usual decision theory formulation. And we put ourselves in a setting where this can already be done. So we consider that there is already an algorithm. So Z here is the data space, and Z infinity means that the algorithm works for like 2 data points, 3 data points, n data points, 100 data points, and so on. So the algorithm works for is well defined for any number of data points, and it produces an action. So the way to think about it is there's the data, dn, that's the data set. Then you run the algorithm on the data. So it's very abstract. It could be anything. It could be minimization, linear regression, empirical risk minimization, linear regression, any algorithm. And then that is evaluated, the performance of the algorithm is evaluated on a loss function. And that potentially also allows kind of, to allow a prediction task, we allow this V, which comes from the some test distribution. And this can also be deterministic. It can be like a parameter, but it can also be a prediction of a future test observation. So this is kind of like a very general framework. And we assume that this can already be done. So that there is an algorithm that for all distributions P in some cast, in some math cal P, in some kind of calligraphic P class, for all distributions of interest, we can control the risk. So this may seem like very, like, is this even possible? But, turns out it's actually very much possible. So for instance, in a hypothesis testing setting, the algorithm, what does it do? It just outputs a binary decision. Do I reject the null? That's a 1. Or do I not reject the null? That's a 0. Okay. So that I will call that phi. Phi dn, it could be phi hat. It's a decision that depends on the data, right? So it's a binary decision, right? And the loss is just the identity function, and there's no test variable. So it's a very simple loss, very simple setting. And turns out with that, what is this? This is just the type 1 error, phi, right? Because this loss just simplifies, just everything is simplified to the phi n. So average value of phi n is the probability of phi equals 1. That's a type 1 error. And so basically, if we are solving a hypothesis testing problem where we have an algorithm for hypothesis testing that can control the type 1 error, that is a special case of our general setting. Okay, so basically that means that whatever we develop in this general setting, we will be able to use it and illustrate it for the hypothesis testing scenario. Okay, is this pretty clear? I think this is one of the, like, it's important to understand, right? We consider a general setting that includes hypothesis testing as a special. It doesn't include everything as a special case. For estimation problems, it's not always kind of arbitrarily possible to set this alpha, because you have the 1 over n, let's say, risk lower bound. You can with a finite amount of data, you cannot just have arbitrary error, right? So, but for hypothesis testing, you can have arbitrary error alpha here. So is this formulation clear? Are there any questions on this formulation? I think it's very important to understand. Okay, so if there are no questions, then I'll assume that it's clear, but please do interrupt me. I'm very happy to take questions anytime, and yeah, make it, yeah. So, okay, so the second setting is that of conformal prediction, which is kind of an emerging area in statistics over the last number of years. So here the algorithm is a prediction set. So given every x, it outputs c hat of dnx. C hat is a subset of the y values of the, let's say, classes or outcomes. And so instead of predicting just one value of y, I predict a set of y values. And how do I evaluate if this algorithm is good? I have an evaluation variable, which is a test data point. It's xn plus 1, ys plus 1. It's not present during the training or calibration phases. And I look at my loss of the prediction set on the xy. That is still a binary loss, a 0-1 loss. And I incur a loss if I did not predict the y to be inside my prediction set. So if I predict a set, but the outcome y is not inside the set, then I incur a loss. So this is similar to a confidence interval, except for the confidence interval, you wouldn't look at a random variable y, a data point. You would do that at a parameter. But turns out in our setting, we can handle actually, we can also do confidence intervals, but that's more similar to this hypothesis testing. There is no evaluation variable there. I wanted to give an example where there is this evaluation variable v. So, and in that case, if I consider this 0-1 binary loss, then what does this thing become? Well, it just becomes the expectation of this, which is the probability of miscoverage. So it's the probability that yn plus 1 is not in the prediction set. There's a dn here at xn plus 1. And I assume that I know how to control it. So it turns out there are methods. There's the famous methodology of conformal prediction initiated by Vladimir Wolfke and his collaborators, and that has roots also in statistics in the works of Wilkes and Wald in the 40s in the tolerance regions. Basically, I just make the interval large, I can assure this, okay? So that's kind of one thing about this framework that we're looking at, is that in order to ensure this kind of this thing that's possible for every alpha, you need to have something kind of like a method that you can always, just make more conservative. Like you make the interval bigger, right? Or here for the type 1 error, you kind of reject less and less and less. Of course, then you have lower power as well. Okay, so anyway, so this is the framework that we consider, but that's just framework. There's no synthetic data yet, okay? So now, how do we use the synthetic data? Given that we have this synthetic, or actually more generally, we can use any auxiliary data set that I'm going to call it d tilde, and capital N will be kind of sort of like a sample size for the synthetic data, and it's kind of written with a capital N to also kind of hint at the fact that it can be much larger than the real data set. How do we construct this kind of algorithm tilde that uses both the real data and the synthetic data, and it's somehow better than the real data, the real algorithm? That's the question. So what do we want for this alg tilde? I guess the first thing is, if the synthetic data is good, it's of high quality, then it should be essentially like having more real data, right? It should be as if I had just n extra real data points somehow. That's kind of the dream scenario, okay? Like, why do I generate the synthetic data? I'm hoping that it's like my real data. Why do I generate, the synthetic images of the long, X-rays? Because I hope that they are like real lung X-rays, right? So it should be like having more real data. But at the same time, there's a tension where, if the synthetic data is of low quality, then somehow this algorithm should not be too affected by the synthetic data. If the synthetic data is really bad, then, if I just pull together the two, the algorithm can behave arbitrarily poorly, right? So somehow I want to guard against this. So these are the two properties that we want. Again, I sometimes I'll just ask you, just like when I teach a course, are there any questions? Please feel free to ask questions if there are. Okay. So, okay, this is just so what we will do is in this setting, turns out we will have our algorithm that uses the real data, and we will introduce a kind of guardrail, and we will use the real and synthetic data together, and we will aggregate it with the Bayes algorithm, the guardrail, and the pooled version. And I'll explain how that works. But actually, in order to define the algorithm, I kind of need to take a step back and explain to you kind of the setting. So it turns out there is a remember that there is algorithm, right? So the algorithm outputs an action or a decision, and we need to be able to compare these actions. The perspective that we take is that we need to be able to compare actions in order to choose which one is the better action. And in order to define what's a better action, we consider it's the one that has a lower loss. So, and to do it kind of completely generally, we take the perspective of a partial order, action space. So partial order is basically, there's two actions, and not all of the actions are comparable, but some of them are comparable. And in addition to that, like one of them is better than the other, and I'll use this symbol. and then also the minimum is well defined. So if I have two intervals, if one interval is included in the other, that's a worse interval, because the interval that's bigger, that will have a lower type 1 error. Like a bigger interval is better, right? And the minimum of the two is kind of the smallest interval that's better than both of them. So in intervals, the union. I will give you these examples. And also, we want the loss to be kind of monotone with respect to this or ordering. So it respects this structure. And this kind of very general, it's satisfied in many inference problems. For instance, I mentioned for confidence intervals, the action space is just subsets of the outcome space. This should be subsets of the parameter space. This should be B of theta in the parameter space. And an action is better than the other if it's included in. I mean, A1 is better than A2 if A1 includes A2, because if you have a bigger interval, that will have a lower coverage, that will have a lower type 1 error. And the minimum is the union. So for hypothesis testing, this is reject and not reject. One is reject. Then is the natural ordering, A1 less than A2. So basically, if I don't reject, then I'm better because I have a lower loss, right? And same thing for predictive inference, it's also like the same ordering. And by the way, it's kind of just a coincidence that I was talking to Armin earlier, and he mentioned in his work, there's a very important, structure, it's partial order. Actually, it's kind of really just a coincidence, but because the kind of structure that we look at is very different. For him, it's more like models that compare. Here it's actions, but it's kind of a testament to how useful this mathematical idea is. So, okay, so any questions on this partial order? So in some sense, if it's too abstract, just think about this kind of confidence interval, for instance, right? A1 is better than A2 if A1 includes A2, because it's a bigger interval, right? It's going to have a smaller loss. So we are not yet evaluating the length. That kind of comes later. Okay, so now what is our algorithm? Actually, it's very different. Very simple. It's very simple. Suppose we have this algorithm that controls the risk. Okay, like a type 1 error, hypothesis testing method, or kind of this conformal method, or some of these other methods. So we do something extremely simple. We do the naive thing where we pull together the real and synthetic data and run our algorithm at level alpha. So this one is kind of what everybody would do, but we know that even though it leverages the synthetic data, it doesn't have any guarantees that it will control the type 1 error, because the synthetic data can be really bad. But now the small tweak that we do is that we take the better of that one and another algorithm, another action, which is just running the algorithm on only the real data at a level that is more relaxed. So there is some epsilon here, and we'll talk a lot about this epsilon, but basically what we do is we think, hey, are you interested to use the synthetic data? Yes. Then in some worst case, you might need to pay a little bit of price, because if you don't pay any price, turns out there's no way to use synthetic data meaningfully. So that's this epsilon. So that's kind of the algorithm here, the merge data, and it's the standard method run at higher level. So this is kind of the abstract definition. Then I'll go in a lot of detail about giving more intuition and examples and so on. But basically, if the real data is similar to the synthetic data, kind of that if this detail is similar to T, then turns out, basically what this does is it just runs the algorithm, the algorithm with a more real data, essentially, right? So it's like free data, free extra data. But if that doesn't happen, if the synthetic data is really bad, then even if this action is a really bad action with a very high loss, no problem, because we are still controlled by this one, right? Even like, think about this as a minimum of two things. So it's kind of the better of the two, okay? If this one is really bad, then this one kicks in. So this one will protect us because it will not allow the loss to go to infinity because it's at alpha plus epsilon, it always controls the loss at alpha plus epsilon. Okay, so are there any questions on the definition of the method?
Can I ask, Edgar, why the epsilon for the second part? Why do you need to do a little bit of a bigger, like widen the one with
Yeah.
the real data?
Yeah, that's a great question, and I'll talk a lot more about it in the future. But right now, so if we um, um, so if we don't have that, then this method will always be more conservative than the alg alpha dn.
Hmm.
So it will control the risk at level alpha, but the only way that it achieves controlling the risk at level alpha is by being more conservative. So in some sense, we want to decouple two effects. One of them is the effect of being good because you're more conservative, and the effect of being good because you have synthetic data. So if I run both of them at level alpha, they're coupled together, and the only reason why I'm good is because I'm more conservative. So
Mm,
we need this kind of little tuning in order to allow us to be conservative due to, I mean, sorry, to quantify, the cost and benefit of the synthetic data. I don't know if that makes
mm.
sense.
I see.
Yeah. Okay. Great. 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 Yeah.
And epsilon is like and this is something that depends on the quality of the synthetic data
Perfect.
generation, or
Exactly. Exactly. So actually, the hardest part of this whole, in some sense, the whole theory is what is the good epsilon to choose. And I think
I
that's what
see.
we still don't. Yeah. But it is. I like the perspective of the cost of using synthetic data. It's like, how much are you willing to pay in the worst case? Because the worst case control is not alpha anymore. It's going to be alpha plus epsilon. But turns out also the benefit that you get is also bigger when you have bigger epsilon. You can have bigger power with this method.
I see.
So finding the yeah, so it's we don't have a perfect answer, but we just choose some reasonable numbers like alpha is 5%, epsilon is 2%, and turns out it looks great. Yeah. So yeah.
Thank you.
Great, great. Thank you very much for the question. Please feel free to ask questions. I'm really happy to answer all the questions. And so,
I have a
it's a very
question as
simple.
well. Sorry.
Yeah, please, please.
So for the previous slide, so I have a hard time to understand why this one will improve the power because let's say if the synthetic data is really dissimilar to the real data, then basically the first let's say the first algorithm with synthetic data will produce a confidence interval that's way off the truth. And then like this procedure is basically taking the union. So basically like if I understand correctly, we essentially union a really bad confidence interval with a potentially good one that will always lower the power, if I understand correctly.
Yeah. So we always take the union of two intervals. And this one can be really bad means it doesn't contribute anything to the coverage, right? So for confidence interval, the notion of power is not so easy to think about. It's like you want to think about coverage, right? So there's coverage and length, right? So for confidence intervals, this one will not contribute anything to the coverage. So only this one will contribute to the coverage, and it will continue. It will have a coverage error of pretty much exactly alpha plus epsilon. So we will have a higher coverage. So we will have just a bigger interval. And then, of course, the interval will be longer. So in the worst case scenario that you described, we will not, like, the synthetic data is really bad. So we cannot hope that much. We cannot hope to benefit that much from it, right? Because the synthetic data is really bad. So the only thing that will happen is we will have, instead of 95% intervals, we will have 97% intervals, and they will be slightly bigger, and they will cover more, and that's it, okay? The interesting regime is when the synthetic data is not exactly the same as the real data, but it's somehow pretty close. That's when I think the benefit will happen, and that's harder to understand and analyze. Does that help?
Yep, that helps us. Thank you.
Yeah, great. Yeah, thank you. Okay, so we have some theoretical results, and they are kind of pretty basic, but I think they're still nice. So, let P and Q denote the distribution of the real and synthetic data, okay? And suppose we have IID data, but, we don't need, IID data, but just to take a kind of statement here. Suppose the loss is bounded by some constant. So remember that we had these coverage losses, 0, 1 indicators. That's C is 1, right? They're bounded by 1. Then this synthetic so by the way, we call it JASP, general synthetic powered inference. This algorithm satisfies the following. The risk is bounded. That's what we want. What is it bounded by? So it's bounded by alpha plus something. It's not bounded just by alpha, okay? It's bounded by alpha plus something. What is this something? It has two terms. Is the best case of two. The epsilon, that's the admission cost, and C times dpq. C is the bound on the loss, and dpq is basically a dissimilarity between P and Q, which is essentially just a TV distance between the outputs of the algorithm when you run it on P and Q. So you can run the algorithm on P, on data from P. You can run the algorithm on data from Q. Those are two distributions, not the original. We don't care about the dissimilarity in the original spaces, only after running the algorithm, because only look at the output of the algorithm. So why is this good? Because if we have very high quality synthetic data, if P is equal to Q, then basically this dpq is 0 or close to 0, is very small. So we then have the risk bounded by alpha. So we still have, the original target essentially satisfied. We don't have any risk inflation. That's great. That's what we want. And even though the dpq is large, we have really bad synthetic data, localized synthetic data, the risk is still bounded by alpha plus epsilon. It's kind of like a robustness statement. If P and Q are close, you benefit from it. But if Q kind of drifts away, at some point you cap it. So I think I personally kind of intuitively think about it as some sort of like a median effect, like a robust estimator where, if you're very far, you don't use it anymore. So that's kind of like that's my intuition. Okay.
Edgar, can I ask a question?
Yes.
So this, I think the intuition that you gave makes a lot of sense. However, what I'm a little bit struggling with is that when I think of synthetic data generated sort of with a generative model, and especially when you think about sort of, because you gave examples of how this could be used in inference, then I think about sort of the uncertainty of that synthetic data, and I don't see how that's coming in this result. I wonder if you could provide any intuition there.
Yeah, great question. Maybe just to clarify, what type of uncertainty are you thinking about?
I mean, just the fact that if you run even the same LLM, you get two different answers, two different times for the same query. So do you have uncertainty for that synthetic data that is being generated?
I see. So that's great point. So that will come in. There's multiple ways in which to think about that. So one of them is that affects what is this distribution Q of the synthetic data. So essentially the Q, like if sampling from the LLM is noisy and there's variability, that means that this distribution Q is kind of more variable. So I will have a larger TV distance here. So it will have a larger, I will have less of a larger bound in some sense, and it will affect my performance. Basically, even in the best case, where some synthetic data that's generated is very similar to the real data, there's variability. That would just mean that even in the best case, you cannot get alpha ever. You always have this dpq larger than 0, so you always have a little bit of inflation. I think that's how it comes in. That's one perspective. I don't know if that helps.
Yeah, thank you. That's helpful. So Q here, I should think of Q, the distribution Q, that in a way that sort of also captures the variability of the synthetic data, not just the sort of the empirical distribution of what I've got in the one run that I've got from synthetic data, right?
Exactly.
Okay. Yeah, thank you. That's helpful.
Edgar, may I ask you a question? I'm still confused. Well, I'm very confused, but anyways, the alpha that you have in there, what is the meaning of that alpha? Is it the risk of the algorithm when you only use the actual data, the DN data?
Exactly. So
Okay?
exactly. Like
Okay, hold on. So in the best possible scenario, I will get the same risk when DPQ is 0. I will get
yes,
the same risk as if I never use the synthetic
yes,
data. So where
yes.
do I see the gain? I mean,
Perfect.
where is
Perfect.
okay?
That's a great question. It's a very sharp observation. That if I think from that perspective, this theorem does not show any improvement compared to the synthetic data. Turns out that can only be quantified through the variability. And we don't actually have any theoretical results yet. We thought about it, but in experiments, so turns out when you pool the real and synthetic data together, you also reduce the variability in the outputs of the algorithm. And that will show up in the plots. And we'll see that basically the algorithm is both more stable and it can reach some performance regime that are not possible with just the real data alone. So for instance, in kind of conformal prediction, at least in the naive version, if I have n data points, then I can get coverage 1 over n plus 1, 2 over n plus 1, 3 over n plus 1, similar to like type 1 error, with n data points, 1 over n plus 1. So, if I just have n real data points, there are certain levels of alpha that I cannot reach without outputting a trivial interval. Right. So basically, that having the synthetic data that's pretty similar to the real data will allow us to reach those levels of alpha that are impossible just with the real data alone. Because it's possible, but you have to output an infinite interval, or you have to always accept. So in some sense,
so can I think? Thinking differently. I would imagine that if I have more data in conformal inference, I will have shorter intervals. I would aim for the same coverage with shorter intervals. But this is not what this synthetic data will gain me, right?
No, and in fact, turns out it's not even generally really true as far as I really know. That because in conformal prediction there is a base level of noise,
Yes,
like
that's
order
correct.
1.
That's
exactly,
correct.
order
Yeah.
1. And
Yeah.
the improvement that I get is a tiny order 1 over n improvement in the length. So it wouldn't.
Okay.
So in general, I would not expect like a much shorter length. That's actually what I'm thinking.
Understand.
Yeah. So
I understand that, but so where is the improvement in conformal inference? Where is
okay.
it?
So for instance, if and I'll show example. If I'm targeting a level of alpha that's 1% with 20 data points, then the only thing that I can do is I can output an infinite interval, for instance. Yeah, and I'll show you a few examples. Hold on, hopefully I get to it in the next.
Okay. Thank you very much.
But it's a very helpful question. Thank you so much. That's great.
Okay, thanks.
Thank you. Okay, so now kind of one additional consideration is that here I really just took a union of two sets, right? So that's kind of potentially it has the like Ali was suggesting it has a potential to become too conservative. So I also need to somehow to kind of guard myself on that side. Like I have a two-sided guardrail. But that's fortunately that's very simple to do, because once we do this one-sided thing, we can also just take the maximum, which is kind of like an intersection of the alpha here. And now you see where the alpha comes in, in our means question, the alpha comes in here. The alpha is kind of like gives me the at most how conservative I can at most how conservative I can be. So that's the final construction of the two-sided case. Basically, I kind of sandwich myself in between these two scenarios. Yeah. So, and this one, basically the output of the algorithm is in between the alpha and the alpha plus epsilon. And further, we have some guarantee on the power as well. now because it's controlled, and we have some similar TV distance-based guarantee. If I have time, I'll explain it again. Okay, so how does this look like? Let's look at for some like hypothesis testing. What I'll do is I run my algorithm at the base level alpha, and I'm looking for a rejection there, or I'm looking for a rejection at the level alpha plus epsilon, as well as at level alpha with the synthetic data. So you can see that I can only reject if I reject at level alpha. Sorry, if I reject alpha plus epsilon, and I will always reject if I reject at level alpha. So I'm always sandwiched in between these two. But turns out, in between, I'm able to leverage my synthetic data, and I'm able to improve potentially power. So let's actually look at this first example of conformal prediction and see how it works in some empirical setting. So in conformal prediction, the goal is given some, as I mentioned, some xm plus 1, given interval such that the probability of the y not belonging to the interval is bounded by some alpha. And there's some version called conformal risk control by Angelopoulos collaborators, where they want not just a 0-1 loss, but an arbitrary loss here to be bounded. So our prediction set, as I mentioned, has this structure. It's always included in it's like this. So our set, the JESP set, is at most as big as the alpha one, and at least as big as the alpha plus epsilon one. And so it has a type 1 error at most alpha plus epsilon, but it can do much better in some cases. So here's a kind of a illustration. We have a lot of illustration in this talk. I probably just have time for one. But basically, we look at this image classification example where the goal is to construct a prediction set of label for the unlabeled images. So the real data is a standard ImageNet data set. And the synthetic data is generated by one of these powerful diffusion models, the Flux model. It's kind of one of the state-of-the-art one. At least when we did this kind of almost a year ago now, but this is one, it's one of the powerful ones. So this is how it looks. This is how a kind of a real picture of a dog, a certain dog breed looks like, and this is a synthetic one. And you can see, they're pretty similar. It's certainly the same breed of dog, but you can see that the environment is quite different. Like, this is the background here. It's much more detailed. You can actually see the fence, and these are much, they are different. And yeah, this is actually a golden retriever. And so we're going to use 30 classes of images. And we're going to use a class conditional conformal prediction where the goal is to have coverage regardless of the true class. So this is kind of an experimental result. So we look at a setting where for each of the 13 classes that we study, there's 15 data points. So this is a very data limited setting. We only have 15 data points per class. But synthetic data, we can generate a lot. We can generate 1,000, okay? So that's very, it's just, burn the GPU, generate a lot. And we're gonna, let the type 1 error, baseline type 1 error to be 5%. And the admission cost, the worst case type 1 error, is plus 2%, so overall 7%. So here are the results. So let's kind of walk through this. So let's look at this. These are a bunch of different classes: husky, retriever, robin, magpie, marmot. So let's look at this class. Here's the coverage and here's the size. So let's look at this class, the Siberian husky. So what do we see here? If we run the Bayes algorithm, that's conformal prediction of 15 data points. At least if you don't use randomization, just use the standard naive version, you will get coverage. Of course, you will get coverage, but it turns out the way that you get coverage is basically you output everybody, because you have 15 data points, you want 95%. So there's no way to get if I because of the kind of quantiles, the statistically equivalent blocks, there's 16 of them. There's 15 data points. There's 16 of them in between the data points. So I cannot get 20% coverage without outputting the infinity set. Infinity here is not actually infinity, it's 30. I output everybody. So I get coverage, but I need to use I need to get sets of size 30. Okay, so that's the Bayes method. Now, what happens if you just use the synthetic data? This is what happens. You will get coverage 60%. It doesn't work. Okay, synthetic data distribution we saw on the previous slide. I guess we didn't see the husky, but we saw it can be really bad. Okay, now what happens if you use JESP, meaning our method? Well, turns out here in blue, you see the target level of coverage. And here in red, you see the alpha plus epsilon, kind of 1 minus alpha plus epsilon, the worst case level of coverage. So you see that we are above the red line. So that means that we do control, as the theory guarantees for us, we do control the coverage at, 93%. Okay, and we have this type of set size of size, something like 5. So, but then you might ask, hey, why don't I just use the guardrail at level, 1 minus alpha minus epsilon, right? I mean, why are, because we are always less powerful than that, right? So why not just use the guardrail? So turns out that one here in this example also attains coverage at the desired level. I mean, of course, it has to, because it's guaranteed to do so, and it has smaller length. So why not use the guardrail? So on this class, there's no improvement. Basically, there's no reason why not use the guardrail. Just because the guardrail is the original conformal prediction at running with 93% coverage. Now that can be done with 15. But turns out, if I look at some of the other classes, then I can see it much more clearly. For instance, if I look at this Labrador Retriever, I can see, in fact, that if I just use the guardrail, I still have 15 data points. I have a lot of variability. Look, in some cases, we ran this experiment many different times, and you know that conformal prediction guarantees the coverage on average over the calibration and the test data point. So for some random calibration data set, the coverage can be much smaller. And in fact, you can see here that the calibration can be 80% or 70% for some cases, whereas we have much less variability. So basically, in this case, we reduce the variability in the algorithm, even though the mean performance is the same. I think this is kind of a little bit to address Andrea's a question. So this, we do not have a theorem about this yet. At least, we thought about it. It's hard to prove, but empirically, we reduce variability. Okay, so are there any questions on this example?
Yeah, could I just had a question about, you mentioned the performance being sandwiched between the two levels, and was that the JESP results should be sandwiched between the 1 minus alpha and 1 minus alpha to epsilon?
Yes.
Because in the plot there, it looked like, for at least, like, say, the Marmot case, it was significantly above. Like, if I'm reading that, it should be between the red and black line.
Oh, no, sorry. It's sandwiched between the two algorithms. So let's see. Let's look at the Marmot. It's sandwiched between the black, the green and the red one. That's what we proved. We proved theoretically that the output is always between the algorithm. It's not between the true levels alpha and alpha plus epsilon, but rather the algorithms.
Great, thanks.
Okay, yeah, thank you. All right, and I think now it's already 3:20, so I ran out of 15 minutes. I'm glad that I got to cover this in detail. I just mentioned, we have examples in protein structure prediction. The goal is to predict kind of the structure of a three-dimensional protein based on sequence. We have a powerful AlphaFold model, and it's good, but it's not perfect. It makes mistakes. Like here, the real one is obviously. And what we are able to do is, let me just show you the kind of picture. What we are able to do is we build on the conformal risk control method from Angelopoulos and collaborators, and we label the parts where we think there is a mistake. So here, the red ones have a mistake. These helices have a mistake. And turns out the question is, can you label them accurately but precisely? Like, label only the ones that have mistakes and not more, because you can label everybody, of course, that's good. So by leveraging synthetic data actually here is already in when you look at carefully at the AlphaFold algorithm, the way it does a prediction, it already searches for some related sequences. We just recycle those, and we are able to achieve here basically we are able to achieve better. I don't think I have such a great picture, but we're able to achieve more precise localization of where the errors are here. So that's kind of what we achieve on this one. Details are in the paper. We have a draft, hypothesis testing. We are able to compare two models with each other, and we use synthetic data from history. We have some guarantee for a two-sided JESP, and so on. We apply it for family-wise error rate multiple testing. It just works generally. So that's all. to summarize, we developed this method, JSP, which is a way to leverage synthetic data for statistical inference in a safe way. It helps when the synthetic data resembles the real data. How does it help? It's application specific, but there's at least two ways. One of them is it reduces variance. For instance, in conformal prediction, we saw it reduces variance. And I didn't show you this because I didn't have time, but for type 1, for hypothesis testing, it can actually improve the power. So we have not achieved a complete characterization of how it helps, but we see it's application specific, meaning application, it means, like statistical problem class dependent on what kind of improvement it can have. But it's the latest version of our paper, which will be in archive in a few days, has the better analysis of the improvements. It has, but at least it always satisfies a guardrail for any synthetic data distribution. So that's good. We're really safe. And obviously it's a nice thing to have. But then there's a question of how to really generate this synthetic data for specific tests. So this is something that I was really inspired by to talk to Shinwei. She has some really great ideas on how to use some how to better generate how to design better generative models. So it's kind of, I think, very interesting to see how to generate synthetic data for specific tasks with statistical inference guarantees. So that's all that I wanted to say. And yeah, thank you very much. Are there any
Thanks,
questions?
Edgar. There's a question on the chat. The question is, should I think the two-sided guardrail is explicitly absorbing all the dependency introduced by the synthetic data into the alpha plus epsilon?
Yeah, great question. I wouldn't think about it that way. It's more like, we just want to make sure that we are not too conservative. Honestly, that's kind of that's the best explanation that I have. Even I've been looking at this for months and months, and we just want to make sure that we are not too conservative, because like Ali was saying, we're just taking a union of two things, so it's gonna get bigger, right? So I have to make sure that you don't get too big. So you have to cap it somewhere. I think even though you have this kind of, if you look at this equation or this inequality, it's really about, this is kind of what you were saying, Shingi, right? That it's kind of like it's really in between those two things. But I think what happens in there's kind of some black, it's a little bit mysterious to me, that I haven't been able to characterize it fully in terms of if there's some variance reduction and what good stuff happens there. Yeah, so I don't think it's the best way to think about it. Yeah. Okay, I see another question from about in official statistics. There's a well-established literature on synthetic privacy preserving disclosure. It's very different. There's potential connections. That's great. So actually, this area that I talked about has connections to so many different areas. Like there's connections to transfer learning, covariate shift, other more general data set shift, and in the papers we have like long literature reviews of all kind of connections. That stuff with the synthetic data for privacy preserving disclosure, I'm not familiar with, but I want to take a look at and try to understand what's the connection. Yeah, so I'm a little bit familiar with kind of standard kind of differential privacy stuff. I think it's not directly connected in any obvious way, even though there's privacy and robustness have some connection, and this is kind of like robustness, but it's not, it's a little bit far away. But I'm interested to take a look at that and see what the connection is, maybe.
Yeah. Hi, Edgar. I had a question on the previous slide, maybe about the sharpness of the results. In some sense, it looks like that your notion of distance between distributions doesn't depend on the loss function L, but I can think that depending on what loss function you use or what you care about, there might be distributional shift that can hurt you more than other, and some of them might not even hurt you at all, right? If I think in terms of robust regression. I wonder if you thought about that or that makes sense at all.
That's a great question. I mean, in fact, we know perfectly well what is the best bound here, and that's just the distance between the expected value of the difference between the two losses, right? So the best bound that I could put there is just expected value of the loss under Q minus expected value of the loss under P. So that's kind of really the best bound. And you're perfectly right that what we have here is very, I mean, it's kind of pessimistic a little bit. Actually, for the maybe I'm going to flip it around a little bit. Your question turns out if you want to learn, like we kind of thought about a kind of follow-up project, which we might do in the future. With is suppose you want to say which data. Suppose I have multiple synthetic data distributions, like multiple generative models. I have historical data. Which one should I use? Well, and maybe it costs me something. Then it turns out that it's possible to kind of design, potentially possible to design a kind of a bandit type algorithm, which kind of looks a little bit at different distributions and samples a little bit and says, oh, it's useful, it's not useful. And for that, we need exactly this loss difference objective. So this one, for that, it's too conservative, clearly. Yeah. So I think that's a great point. We just wanted to have something like that's very general and very abstract. Yeah. But yeah,
Makes sense. Very nice talk. Thanks.
Great. Thank you. All right. Great. Yeah. Thank you everybody for asking all these wonderful questions and for paying attention. And I apologize I cannot be there. I hope to meet you. Maybe as we were talking with some of the faculty earlier, maybe I can drop by during your JSM reception. So then I get to meet many people in person. So that would be great.
Edgar, there seems to be one more question. Maybe
there's one question.
I just ask another quick question on this slide. So basically, do you have any intuition why these distribution measures come in like a minimum way instead of like an additive form to this like the error control?
For sure, yes. That's by design. From the very beginning, you remember that from the very beginning, what we said to ourselves is that we want to choose the best of two actions that have the lower loss. And remember that we chose the action in a way that is the minimum of the two, like meaning the better of the two actions. I either use my synthetic data or I don't use it, but I allow myself a little bit more risk. So that's the reason why it comes out in a minimum way, because it's from the very beginning, from this definition. That's kind of by design, yeah. Because I either choose this one or that one. I don't do both of them simultaneously. Yeah.